Ladies and gentlemen, good evening and welcome to another session of Nambani Academy, grade 11, physical sciences. And we are currently running a series of videos, lessons on quantitative aspects of chemical change. So today we will be now continuing from part 1, which is now what we did yesterday. So we'll basically now be continuing with that. But before that, let me just maybe quickly check if everybody is here. But Anetse, how are you?
Oh, I'm good, sir. Thanks for asking.
Thank you very much. Lesedi?
I'm good, sir. Thank you.
Thank you very much. Neo?
I am doing well, sir. Thank you.
Thank you very much, Your Excellency, Mr. Nyokong.
I'm good, sir. Thank you.
Thank you very much, Mr. Nyokong. Let me check who else is not here. Ratanang Phehlo.
I'm good, and you, sir?
I'm doing very well. Bonolo.
I'm fine, sir. Thank you.
Thank you very much. Moteo. I don't see Moteo. Okay. And then the last one should be Lesedi.
Oh, sir, you already greeted me.
Oh, okay. Thank you. Ladies and gentlemen, let's start. Let me just try to locate Moteo, and we will be good to go. CTD. Ladies and gentlemen, let's start. But before we start, let's just have a quick recap of everything that we did now yesterday. We explained basically what is quantitative aspects of chemical change. We looked now into the teaching plan, which is the annual teaching plan of basically what is it that we need to know when we are looking or doing this particular topic, quantitative aspects of chemical change. So the thinking is we plan and intend to address all the bullets that are on the ATP. Later, when all the concepts has been attended to or explained in detail, we are just going now to emphasize on more of the approach in the exam. Why is that the case? Because now we are expected now also to perform certain calculations that relate now to concentration, calculate concentration in mole per decimeter cubed, determine the percentage composition, empirical formula and the molecular formula, do now stoichiometric calculations, including the limiting reagent. So for today, we are not going to do limiting reagent. We are going to cover bullet now for week 3, bullet 1, 2, 3, and 4. And then tomorrow is then that we are going to incorporate that with the stoichiometric calculations of the limiting reagent. So that is the only new part that will be there in grade 11 syllabus. The reason for that is I want us to build basic principles of stoichiometric calculations before we can introduce complex stoichiometric calculations that will involve the limiting reagent. So without wasting any time, let's move now into basically what we did yesterday. We explained the mole concept. We explained now the relationship between molar mass, and the mole, where we used now the equation N is equals to M over molar mass. From that, we also used now the Avogadro number, where we explained now using the Avogadro number that 1 mole basically represents now what? 6,02 multiplied by 10 to power 23 particles. And that can now differ depending on what are we looking into. Is it molecules? Is it ions? Or is it atoms for that matter? So that is going to assist us in terms of building a solid foundation. Now I'm waiting for your screen to show the slide that I'm on, such that now you can basically see what is that I am referring to. I'm trying to check what could be the problem. There we go. Mole concept. We explained this concept, and then followed by molar mass and relative formula mass. We did perform few calculations relating to molar mass and relative atomic mass. I was very happy with that. We explained now relative atomic mass in terms of what it means when one refers to relative atomic mass. We said it focuses more on the isotopes, and isotopes are known as atoms of the same element with the same atomic number but different mass number. We did now an example here, which was a problem that I chose for us to be able to perform, where we identify element Q, and we found that was a neon. The Avogadro number explained also in detail. We showed now the relationship between the number of moles as well as the Avogadro number. Very, very happy with that. That's when we did now calculations relating to Avogadro number and the number of moles. So the basic stoichiometric calculation that I'm going to refer to will want us to be on the lookout for this formula as well as this formula here. So the two formulas are going to be very, very key when it comes now to the stoichiometric calculations that we are going to perform. Let's move. This was just an example that I wanted us to do, but it will not matter. I want us to come to this particular slide. So today, that is where the lesson is going to start. We are going to refer now to molar gas volume and the STP. Now the question will be, what is an STP? STP is standard temperature pressure. So when we say that we are working with STP, the examiner should tell us that we are at STP. One cannot just assume that everything is at STP. The examiner or the information given in the stem of the particular question paper will refer now to STP. So once it is at STP, ladies and gentlemen, we will be able to use what we call molar gas volume. What is molar gas volume? Molar gas volume, ladies and gentlemen, is basically a volume of a gas at now STP. But that volume of a gas is represented by 1 mole. Hence the word molar gas volume. So 1 mole of a gas occupies a volume of 22,4 decimeter cubed at STP. So this here now becomes our standard molar volume, which is 22,4 decimeter cubed. But now that is when we have, or we are told that we are at STP. So now, ladies and gentlemen, let's check what is happening here. 1 mole of NH3 gas contains 6,02 multiplied by 10 molecules at STP. That we know in terms of the Avogadro number. When we look at the gas also, which is oxygen in this instance, it will still have the same number of molecules at STP. But I am interested in what does 1 mole means in terms of the volume itself when we are at STP. So 1 mole of helium has now what? 22,4 decimeter cube at STP. 1 mole of oxygen gas has now what? 22,4 decimeter cubed of volume at STP. Now I am going to add an example here to say, now fine, 2 mole or moles, let's write mole, of oxygen has decimeter cubed at STP. What should be done in this instance? It's very easy. One must just multiply the volume of 22,4 with what? With 2, and that will give us something like 44.8. So 2 multiplied by 22,4, this will give us now something like 40. Let's check, connected, restored. Thank you very much. Baanetsi, can you hear me, lady? because it seems like I lost connectivity at some stage.
Yes, I can hear you, sir.
Thank you very much. Reconnection successful. Thank you very much. Then I can go back to my screen and continue. Sorry about that. Connected now fully. Where do I get this information here? I got this information of 2 mole of oxygen has 44.8 decimeter cubed at STP by using the equation N is equals to V over Vm, where Vm is just molar gas volume. And remember, ladies and gentlemen, this is now at STP. And the volume must be now in decimeter cubed. Ladies and gentlemen, let me emphasize and say, we can only use this equation for gases only. If it's not a gas, this equation will not apply. We need to ensure that everything that we do, especially working with this equation, N is equals to V over Vm, must now be when we work with a gas molecule. That is very, very, very important, ladies and gentlemen. If it is not a gas, then we cannot work with this equation. Hence, I am saying the emphasis should be we are working with a gas molecule or a gas for gases only. It's very, very, very important. So let's highlight that for us to be able to remember and know that it is only for gases. So we have introduced equation number 3, which is N is equals to V over Vm. And that now has been explained in detail. It basically says, let me give you your 30 seconds for one now to digest everything here. Thank you very much. I don't see any hands, comments. Maybe let me just check. Lwandle, are you still okay?
Yes, sir.
Thank you, Neo.
I'm still fine. Thank you, sir.
Thank you, Your Excellency, Mr. Nyokonya Kallo.
I'm still good, sir.
Thank you very much, ladies and gentlemen. Let's move. When we move, we expose ourselves now to the concept of concentration. Concentration is defined as the quantity dissolved in solid in mole per decimeter cubed of a solution. You will get different definitions relating to this one, but just ensure that when you explain it, it should have now be the quantity of a solute in mole per decimeter cubed of a solution. Ladies and gentlemen, the equation is straightforward. It's C is equals to N over V. So it is the very same equation that relates also the number of moles. So what does this say to me in general? It says now everything looks like it is surrounded by the mole concept. So the emphasis should now be on the mole concept itself. So once I can calculate the number of moles, ladies and gentlemen, it will be easy for me now to calculate or perform calculations relating to any of the chemical quantities. C is equals to N over V, and the emphasis is our volume must be in decimeter cubed. This second equation, let's write this one as 1, and let's write this one as 2. This second equation, ladies and gentlemen, I want to say it is accepted and not accepted. I don't know if that makes sense. At times, we want to see the build up to the answer. At times, we award a mark for multi-steps. What does that mean, that number? This means now N is equals to M over molar mass. C is equals to N over V. So what we want to see and check is a direct calculation that will come and explain now this side of C is equals to N over V. That is very, very, very important, because now when the equation is like this, we are not necessarily sure if we should award a mark for the final answer of mole, because the only final answer that you are going to have will be the final answer of the concentration in mole per decimeter cubed. So what I want us to do is, let's expose ourselves to the multi-step. While multi-step is going to assist us also when we get into the limiting reactant, when we get into the complex stoichiometric calculations. So ladies and gentlemen, I have one easy example here. I am going to give you now 2 minutes before I can get into it, such that we can check where we are in terms of calculation of the concentration. So with that being said, your 3 minutes starts now. Ladies and gentlemen, thank you very much. One more answer. Outstanding. Kindly send so that we can easily and quickly discuss. Just one, just one, just one, just one. And we can quickly discuss. Received. Thank you very much. Ladies and gentlemen, let's go straight into it. The tricky part here is, remember, the emphasis is on our volume must be in decimeter cubed. So the only catch here was the volume is given in 250 centimeter cubed of water. So what must be done? First thing is V is equals to now 250 centimeter cubed divided by 1000, and this will be something like, let me quickly check. This will be something like 0.25 decimeter cubed, because we divided now by 1000. Then it's easy to say I am given the number of moles, very easy, so I don't have to calculate the number of moles. So this becomes now C is equals to N over V, which is just equals to 0.2 divided by 0.25. 0.2 divided by 0.25, and then it will give you an answer of 0.8 mole per decimeter cubed. Very, very, very important, ladies and gentlemen. So that is now the basic concept of now concentration. What does this mean to me? It means I have attended to all the challenges that I have. So with the challenges that I have, I am going to duplicate the slide quickly and just have a blank sheet. Why do I need a blank sheet in that number? I need a blank sheet because I want us to develop a system or a strategy that one can use. The strategy says, I am expected to calculate the moles of A. But what is this moles of A? This moles of A will be now given. Very, very, very important. So somehow I will be given the number of moles. The question will be, how best can I calculate now the number of moles? Ladies and gentlemen, that is where the tricky part comes in. I can calculate the number of moles from N is equals to M over mass. But when am I going to apply this? When I am given the mass. Can I use another equation? N is equals to N over NA? Of course I can, because it also has now what? The element of mole concept. So I can use that in order to get the number of moles. So the critical thing is getting the number of moles over NA. And when am I going to use the Avogadro number? when I am given the number of atoms, when I am given the number of molecules, when I am given an ion, then I can apply N is equals to N over Na. This will apply when I have now what? Let's just say particles for now. But particles, ladies and gentlemen, can represent any ions, molecules, as well as atoms. Can I be able to calculate the number of moles also? Yes, N is equals to V over Vm. When will this be applicable? First thing, when I am told it is at STP, and when it is now for gases only. Can I somehow also calculate the number of moles? Of course, when I have C is equals to N over V. This is now what? When I have concentration given to me. So all these equations are equations that are going to assist me in terms now of what? Sorry, of getting the number of moles. Ladies and gentlemen, the number of moles is the stoichiometric calculation foundation. Everything will be based on the number of moles. This strategy works through the chemistry of grade 10 until the chemistry of grade 12. But what are we going to do? We are just going to put emphasis on what is it that one needs to look for. What is the aim here? The aim is I want to cross the bridge. Why cross the bridge or cross the bridge? Because what the examiner has assessed or asked me have not given me any valuable information relating to that. So at an instance, I am going to calculate the moles of B. And this moles of B is what we call now the unknown, the question, the one that is being asked. So if I can get the number of moles of B, I can perform and do everything, ladies and gentlemen. Can we say if I have the number of moles, I can calculate the mass with M is equals to that. Can I calculate the number of particles? Yes, with N is equals to Na over N for particles, molecules, and now atoms. Can I get the concentration? Yes, C is equals to N over V. Can I get now volume? Of course, N is equals to V over Vm, and this will assist us for the volume. What is the catch? The catch is how do I cross the bridge? The catch is how do I cross the bridge? Ladies and gentlemen, I cross the bridge by using what we call the molar ratio. The molar ratio is the only assistance that I have to move from the given to the unknown. If I do not have the mole ratio, I will not be able to cross that bridge. The mole ratio will also assist in determining the limiting reactant. But what is critical now? What is critical is for me to cross this bridge, I need now what we call molar ratio. The molar ratio comes from the balanced chemical equation. If you do not have a balanced chemical equation, ladies and gentlemen, you will not get the correct answer, because the molar ratio comes now from a balanced chemical equation. That is the only tool I have for me to link the given to the unknown. We are going to modify and add more to this particular slide immediately when we introduce the limiting reactant. But that will be easy. Why? Because our foundation of the stoichiometric calculation is very, very solid. So this approach will be what we call for stoichiometric calculations. So the calculations, ladies and gentlemen, will always differ because it is an exam, it is an assessment, it is a form of calculations that we are expected to perform. Remember, when we started, we said quantitative aspects basically means what? Basically means measure in terms of the substance. So when we perform the stoichiometric calculation, it's either we are going to calculate the mass, it's either we are going to calculate the volume, it's either we are going to calculate now the concentration, or even now the number of particles. Ladies and gentlemen, let me give you your 30 seconds to digest the concept of stoichiometric calculation. Ladies and gentlemen, this is my thoughts, my approach. It will not necessarily say it is cast in stone. You can modify in order for you to be able to understand and to know exactly how you can approach more complex problems in the stoichiometric calculation. Ladies and gentlemen, your 40 seconds starts now. Thank you very much. I do not see any hands, inputs. Let me quickly check. Ba'anezi, are you fine?
I'm still fine, sir.
Thank you very much. Lesedi?
I'm still good, sir. Thank you.
Thank you very much. Then, ladies and gentlemen, let's move. This is empirical formula. We will come to it later. What I am interested in is this particular calculation. the calculation says calculate the mass of oxygen obtained when 14.7 grams of potassium chlorate decomposes completely to form potassium chloride. What is tricky here is we need to have a balanced chemical equation. This is grade 10 work to say what we have potassium chlorate that decomposes completely to form potassium chloride. So the very first thing that one must do is to ensure that you know the name of potassium chlorate or the formula for that matter, the formula also of potassium chloride, very, very important, because without that, we will not be able to perform any stoichiometric calculation relating to this. So potassium chlorate is it's KClO3. Just waiting for this pen to respond. KClO3. But now it decomposes completely to form potassium chloride. So let's write that equation. The equation will be KClO3 giving us KCl2 and oxygen. So I am going to give you the equation. Kindly balance it quickly for us so that we also now check the level of balancing from grade 10. Let me just quickly write it down. It is now potassium chlorate, KClO3, decomposes into KCl2 plus oxygen. Ladies and gentlemen, I'm just going to give you a minute for you now to just balance this particular equation, because if it's not balanced, we are not going to be able to get it right. Kindly and quickly assist in terms of balancing this particular equation. Ladies and gentlemen, thank you. All answers received. Let's now try and explain. If I multiply here by 2, that will mean 2K, and then multiply by 2K, Cl2, Cl2, and then 2 multiplied by 3 will be 6. Then I can just multiply here by 3. Then my equation is balanced. Ladies and gentlemen, it can be any other coefficients. I do not have a problem as long as you can easily check yourself whether your equation is balanced. It can be 4, 4, 6, 100%. Any multiple that you can have that will basically give you the same number of potassium atoms, the same number of Cl atoms, as well as oxygen atoms. But what is the catch here? We are given the mass of potassium chloride. So I'm going to write down the mass of KClO3, which is just 14.7 grams. According to our strategy, the only best thing that one can do is I am given the mass. So the strategy says if I am given the mass, I must basically get the number of moles. So to get the number of moles, it will mean I need to calculate the molar mass. Let's check if one can get the molar mass of KClO3. I am just giving you a minute, ladies and gentlemen, for you to do that for us. The molar mass of KClO3, the molar mass. Let me give you just a minute for you to perform that. Thank you very much. Answers received. So this is very easy. Hence, we explained the important concepts thereof. KClO3, this is just now 39 plus 35.5 plus 3 multiplied by 16. This gives you something like 122.5 SI unit. Very, very important, ladies and gentlemen. Can I now calculate the number of moles? Of course, the number of moles of KClO3 is equals to M over the molar mass, which will just be KClO3, which is equals to 14.7 divided by 122.5. Use a calculator. 14.7 divided by 122.5. and this will give me 0.12 mole. But now that is the number of moles of potassium chlorate. Let's go back to this strategy here. The strategy says, okay, fine. I have calculated the number of moles of the given, which in this case is potassium chlorate. What do I need in order for me to get now the moles of the unknown? What is the unknown in the question? The unknown in the question is oxygen. So I am moving from the given to the unknown. But before I can get the number of moles of oxygen, which is the unknown, ladies and gentlemen, I must cross the bridge. How do I cross the bridge? By using the molar ratio. Then I am going to go into the problem again and basically just check if we are able to use the mole ratio. The mole ratio comes from the balanced chemical equation. So the balanced chemical equation will assist in us getting the moles of the unknown. So let's quickly do it and check if we can use that. Then I'm going to say N of KClO3 over now N of oxygen is equals to 2 over 3. Yes, Lesedi.
Sir, on your screen, I can only see percentage composition.
Oh, okay, sorry. Lwandle?
No, so I was gonna say the same thing. It was just
The same thing.
Yes.
Okay, so now it says mass.
Yes, sir.
Thank you very much. Sorry for that, guys. Now it basically says this 2 and 3 basically comes from the balanced chemical equation. And that is what we call the molar ratio. But why do we need the molar ratio? Remember, we said we need the molar ratio only because of we want to cross the bridge between the given and the unknown. The unknown in this instance is oxygen. That is the reason why the focus is now on oxygen only. Then I am going to do the mathematics, cross multiply. And this will be 2N of oxygen, which is equals to 3N of KClO3. What must I do now? Basically just substitute, multiply by 3 and divide by 2. So N of oxygen, kindly check my answer, please. It's 3 multiplied by 0.12 divided by 2, and then I get the number of moles of oxygen as 0.18 mole. But I got the number of moles. But the question is asking for calculate the mass of oxygen. So that is the number of moles. It is not the mass. What must I do? I must now say which formula do I have that can correspond to the mass. It's N is equals to M over molar mass. And this will be 0.18. Mass is what I am looking for. The molar mass of oxygen is 2 multiplied by 60. And then I'm going to use a calculator. Multiply by 32. I get my answer as M of O2 is just equals to 5,7676 grams. And that is now my final answer. Lesedi?
Sir, can you please explain again, what did you do there by the 2N of oxygen is equal to the 3N of potassium chlorate?
Correct. Okay. What I did there, let's just start. Do you understand where the 2 and the 3 comes from?
Yes, sir.
Thank you very much. So you relate the 2 or the coefficient with the actual substance that you are working with. So what you do is you basically just cross multiply. So if you multiply NO2 by 2, it will give you 2 NO2. Then you multiply the N of KClO3 with 3, it will give you this particular part. Then in between, let me use red pen. In between this step, you have 2 NO2, which is equals to 3 multiplied by 0.12. The 0.12 is basically the number of moles of KClO3. So 3 multiplied by 0.12 gives you something like 0.36, but you still have 2 N of O2. What do we do now? We divide both sides by 2, divide by 2. This will cancel. The number of moles of O2 will be equals to, divided by 2, will be equals to 0.18 mole. So that is now an intermediary step that one must be able to perform in order to get the number of moles. Inputs, Lesedi.
Thank you, sir. I now understand.
Thank you very much. And ladies and gentlemen, let me just maybe quickly get a reflection from Mr. Nyokong. Let me start with you. Inputs for today's lesson, sir.
Sir, I think today we learned a lot about stoichiochemistry, sir.
Thank you very
that's all
much.
I have for today, sir.
Thank you very much. Bunolo? Inputs, please.
Sir, I learned a lot today. I just got a bit confused here at the end, but now I understand.
Thank you very much. Lesedi, covered. Lwandle?
Yes, so I'm actually very happy with today's lesson. We covered a lot, and I think it was good. It was understandable, and the content wasn't like too overwhelming. But like, it's nice to see how everything links.
Thank you very much. Ratanang Phehlo.
So I really enjoyed today's lesson and understood everything that you have taught. So yeah.
Thank you very much. So we are building towards complex grade 11ish science. We are actually there already, but the thinking should be we need to solidify the understanding of the stoichiometric calculation. So tomorrow, ladies and gentlemen, we are going to introduce a concept of now mass and volume. And immediately thereafter, introduce the concept of limiting reactant. But now I am going to give you now this mass volume as part of the activity for tomorrow. So this will be your homework. Kindly send it before 11 a.m. tomorrow. But I will write also in our group. Ladies and gentlemen, with that being said, it brings us now to the end of today's session. Why is it not until 7:30? Only because we build with basics. We don't want now an overwhelming content of too much information at the same time. So today, work on the idea of mass volume as well as now molar gas volume at STP. If that is covered, believe you me, I am very, very happy. Ladies and gentlemen, from me to you, thank you very much, and let's meet tomorrow at exactly 17:55.
Thank you, sir.
Bye, sir.
Thank you and bye, sir.
Bye, sir.